First, I'll be presenting on the project background first. In modern power plants, boilers play a key role by converting water into steam. Controlling the drum water level is crucial to avoid hazards like boiler dry out or water carryover. This system is nonlinear and complex, requiring proper modeling and control. The main objective of this project are, first, to develop a dynamic model of the boiler level system. Second, to apply linearization techniques. Third, to analyze the system dynamic behavior. And finally, to design a suitable controller using PI, or PID methods. This project focuses only on the level control loop of the boiler system, which is treated as a single input, single output or SISO system. We assume ideal sensor and actuator behavior and neglect delay, noise, pressure, and combustion effects. The control system is based on a feedback loop from the PNID provided by Prof. Madya TS Dr. Hui Shin. It includes a level transmitter, level indicator controller, and a control bar for the inlet feed water.
So here is a plot diagram representing a closed loop feedback control system. This is how we maintain our desired water level. So a closed loop system means that the output of the process is continuously measured and feedback to the control loop, allowing for the real-time adjustment. First, we have the set point, or we call it as the desired level. This is our target water level, the ideal state we want to achieve and also maintain. So it is set by an operator or even automated system. Next, the controller, labeled 0005 in our diagram. So this is like the brain of our system. Its job is to compare the desired level with the actual measured level. Based on this comparison, it will calculate error, which is referred to the difference between what we want and what we have. So it's called like to minimize this error. Following the controller, we have the valve 0005. So this is actually our actuator. The controller will send signal to this valve, which then adjust the flow of the feed water into the boiler. If the level is too low, the valve will open more, and if it is too high, it closes. And then the boiler itself, this is our process unit. It is where the steam is generated and importantly where the water level must be precisely regulated. And last, we have the transmitter 0005. This is our sensor. It measures the actual water level inside the boiler. And the important information is then sent back to the controller, completing the feedback loop. This continuous measurement and feedback is what makes the system closed loop and allow for the dynamic adjustment.
To simplify the modeling, we made several assumptions. First, we focus only on the liquid phase and assume constant pressure and temperature. The drum is assumed to have a uniform cross-sectional area and well-mixed water with constant properties. There are no sensing or actuation delays, and we treat steam outflow as a disturbance, so ensuring effects are neglected. The key parameters are cross-sectional area equals to 10 square meters, bath gain equals to 10, steady state equals to 2 meters, and outlet coefficient equals to 10. From this, we calculate flow resistance R equal to 0.2828, and time constant equal to area times with the flow resistance equal to 2.828 seconds, and steady state gain K equals to 2.828. To derive the dynamic behavior of the system, we begin by establishing the relationship between the volume of water in the boiler and the water level, which is simply the cross-section area multiplied by the height. When we differentiate this relationship, we obtain the rate of change of the water level over time. Then accumulation of water in the drum is equal to the inflow minus the outflow. By substituting the flow expression for both the nonlinear first-order differential equation as shown on the slide. The equation captures how the water inside the changes in response to the feed water valve outflow. To apply classical control design technique, we first need to linearize the nonlinear model of the system. This is done by defining deviation variables around the steady state values for both the water level and the valve signal as shown in the slide. Next, we then apply a Taylor series expansion to approximate the nonlinear square root term, which simplify the model into a linear form. After substituting and rearranging the terms, we obtain a linearized differential equation that describes the dynamic behavior of the system. That is important because it allows us to move forward with standard control design and stability analysis. Next, we rearrange the linearized equation by dividing everything by the area of the boiler. This gives us a simplified form, as shown in the slide, which highlight how the rate of change in water level is influenced by the valve signal. We then define two important parameters, the time constant, represented by T, and the steady state gain, represented by K. This equation now clearly shows the system as a first-order dynamic model. It allows us to analyze how the boiler level responds over time to changes in the valve signal, and it sets the foundation for the next step, deriving the transfer function. To make this model easier to work with, especially for controller design, we convert the time domain equation into the Laplace domain. After applying the Laplace transform, we arrive at the standard transfer function form as shown in the slide. By substituting the calculated value of the time constant and gain, the transfer function simplifies into a clean expression that represents the dynamic behavior of the steam drum level system. This first-order transfer function will now be used for system analysis.
Next is the step response and time domain characteristic for our system. So our system is modeled as a first order dynamic system with the transfer function as below, Gs equal to K divided by tau s plus 1, where K is the steady state gain and tau is the time constant. And when the system is subjected to a step input, such as a sudden change in feed water flow, the water level response in the time domain is as below, Ht equal to K in the bracket 1 minus exponential of E T divided by tau. This means that the water level rise smoothly and exponentially towards a new steady state value. Then let me explain this graph, which illustrates a typical first order step response. So the x-axis will represent the time, while the y-axis will represent the water level. At the time 0, the water level starts at the initial value, which is assumed to be 0, and the curve will rise exponentially and approach the final steady state level, which is K. And then the time constant, tau, is marked on the time axis at the point where the response rate at approximately 63.2% of the final value. And then these are the key time domain characteristics. From this response, we can identify several important characteristics. For the first characteristic, steady state value, which refer to the final water level after a long time, the approximate value is K, which is equal to 1. And for the time constant, tau, it's referred to the time to reach 63.2% of the final level. The approximate value is tau, which is equivalent to the 2.828 second. And for the rise time, refer to the time to rise from 10% to 90% of the final value with the approximate value of 2.2 tau. This value is equivalent to the 8.48 second. And for the settling time, refer to the time to stay within 2% of the final value with the approximate of 4 tau. The value is equivalent to 11.31 second. And for this system, there is none overshoot in the system because it is in first order, and the steady state error is 0 because it is type 0 system. Moving on the system type and order, our system is classified as a type 0 first order system. For the system order, the order is determined by the highest power of S in the denominator of the transfer function. In our case, Gs equal to K divided by tau S plus 1. And when it is simplified, it becomes Gs equal to 1 over S plus 0.353. So it is actually a first order system. For the system type, The type is defined by the number of pure integrators, which is the poles at the origin in the open loop transfer function. Since there are no poles at the origin, our system is type 0. This means that the system responds quickly and also smoothly to the set point change or disturbance, and it also can eliminate steady-state error for the step inputs, but not for ramp or higher order inputs.
So 4.3 is stability, analysis, pole roots, and damping. And the transfer function is 1 over s plus 0.353. So we know that if we want to determine whether it's stable or not, s must be smaller than 0. So the s is negative 0.5353, and then we know that it is a negative root and it is located in the left hand of the s-plane, which means that this system is stable. And since there is only one real root, there is no oscillatory behavior, and the damping is not a constant here because there is no imaginary component. So this system is exhibit a monotonic approach to the steady state value without overshoot or oscillation. In this system, disturbance such as like sudden increase in steam outflow rate can actually affect the boiler water level. So this model is the system response to such disturbance is governed by the time constant t equals to 2.828 second. A larger time constant means slower response, while the smaller time constant means faster recovery. Since this is a first order system, so it will eventually reach a new steady state level after a disturbance, but may exhibit lag depending on the disturbance magnitude. This is due to the lack of the absence of integral action in this model, means the system cannot completely reject steady state error caused by disturbance without additional control. In this 4.5 is the discussion for this part 4. For this part 4, we identify that this boiler is a simple and first order system, is easily to control, and it is stable and exhibit predictable behavior. But however, being type 0, it is prone to steady state error under constant disturbance, indicating the potential benefit of adding integral action through a PI or PID controller in later stage. The linearized model does not capture complex dynamic like swell or noise. So while using the controller design, real-world tuning might require adaptation. Overall, the model is effective for initial analysis and controller selection, forming the basic for the next stage, which is tuning and implementation.
So after having some calculation and also discussion in previous part, we're here for controller selection part. So we have three types of controller, which is P, PI, and PID. So the function of this controller will be discussed in this part. So the first one is proportional controller. Proportional controller is only for proportional. The transition response is fast reaction but maybe offset. The overshoot is generally low, and it is limited for first order system, which steady state error remains. And this controller is to control gas pressure and also liquid level. Second controller is PI controller. PI controller indicates for proportional and integral. The response for this controller is lower than P and moderate rise time. The overshoot is also moderate, depends on tuning. It is highly suitable to remove offset for first order system, and this controller is suitable to control flow. The third controller is PID, which indicate proportional, integral, and derivative. So the response is fastest response and reduced overshoot. It can minimize the overshoot effectively, and also it is often unnecessary for first order system because it's overkill for a slow non-oscillatory system. And also this system is suitable to control temperature and also composition. So based on these three types of controller, we would like to choose PI controller as our controller in the system. The justification in our selection is because the process in our system exhibit first order lag dynamics without inherent integrating behavior, resulting in unavoidable steady-state errors when subject to step disturbance if only a proportional control is applied. Introducing integral action allow the controller to eliminate this offset by accumulating the error over time and adjusting the control input accordingly, while PID control could further improve tension performance. The system does not display significantly oscillatory or higher order behavior that would necessitate derivative action. Moreover, derivative terms could amplify measurement noise from the level transmitter, leading to undesirable control variability. Therefore, the PI controller achieves an optimal balance of accuracy, disturbance rejection, and implementation simplicity for this application.
For the calculation of tuning, in this project we will use Cohen-Kun because it is more precise controller for time delay and process dynamic. It also structured and reliable tuning approach that enhance control performance without excessive trial and error. In this table here, show the formula to calculate the Cohen-Kun for P, PID, and PI controller. To calculate the Cohen-Kun, we need the time constant and also the date time. Hence, in this calculation, we will use the Smith and Collar method to find the date time and time constant, which is T1 correspond to 35% and T2 correspond to 85%. From T1 and T2, we use to calculate the date time and also time constant. From the date time and time constant that has been calculated, next we will find the proportional gain and also the integral time for the PI controller using the formula stated above.
So in conclusion, the feedback control system designed for steam drum water level based on the first order dynamic modeling effectively captures the essential system behavior and enable precise regulation of the water level. The first order models that respond as well as the time domain characteristic provide clear insights into system dynamics and also facilitating straightforward controller tuning to achieve stable, smooth, and accurate control. This approach actually ensures safe and efficient boiler operation by maintaining the water level within the desired limit despite disturbance, and this demonstrates the practical value of combining simple dynamic modeling with feedback control principle in industrial process control.